I want you to imagine a field of wheat. There's a breeze rolling over the ocean of amber grains, and as you close your eyes, you can almost imagine the taste and smell of fresh baked bread. Now, when you open your eyes, you notice that what you previously perceived to be flowing amber hills are now stark white and frosted tipped. This is the scene that greeted farmers in Zambia in 2017, Bangladesh in 2016, and several South American countries in the 1980s and 90s. But what if I told you that the culprit for causing this disease also causes disease in rice, oats, barley, and over 50 different species of grasses in 85 different countries in the world? Magnaportha oryzae is a global fungal pathogen that has been able to outwit and outmaneuver any attempts to create resistant plant cultivars to this fungus. And part of this is because, like any good pathogen, it is able to quickly adapt and evolve to its changing host and environment. Within the genome of this fungus exist genetic elements called transposable elements, which are able to move and insert themselves in other regions of the genome. Transposable elements are typically found near chromosome ends called telomeres. And this region is especially important because it experiences frequent mutations and rearrangements, which increase the rate of evolution and adaptability within this fungus. Now, part of the frequency of these rearrangements at telomere ends is due to the insertion of two transposable elements called motors that are inserted within the telomere. These cause frequent breakage and repair events. Now, interestingly, motors are endemic to telomeres, but we see instances of fossilized inactive motors within the interior of the genome. I study these fossilized sequences and their history of chromosome end rearrangements in the genome. And of the 10 strains that I examined, I saw that even among closely related strains, there was a high degree of variation where several of these sequences had been deleted. And even more interestingly, within four of the strains I examined, deep within one of their chromosomes is a population of these fossilized motor sequences that suggests that there may have been a chromosomal fusion event that took place where the ends of two different chromosomes came together and joined. The results of my study illustrate the highly dynamic nature of these chromosome ends and how they might play a role in the success or evolutionary success and pathogenicity of this global pathogen.